Our first speaker is Dr. Stephanie Simmons. She's joining us online all the way from across Canada. Dr. Stephanie Simmons is an associate professor, Canada researcher, and C4 Quantum Information Science Fellow based out of the Department of Physics at Simon Fraser University, and is the founder and chief quantum officer of Photonic Inc. Her work on silicon quantum technologies was awarded the Physics World Top 10 Breakthrough of the Year of 2013, and again in 2015. And she's one of the only 5 individuals to have ever won this award twice. She was named one of Canada's top 40 under 40 for 2022, and her work has been covered by the New York Times, CBC, BBC, Scientific American, and The New Scientist, and many others. Everyone, please welcome Dr. Stephanie Simmons.
I'm going to keep to time. I have a hard stop at the top of the hour, so I will kind of catch up a little bit. And yes, I do thank you very much for the invitation to speak, and for those of you who stuck around to hear me talk about it. I'm going to do quite overview discussions here, because what we're talking about is really big, actually. Quantum computing and quantum technologies are really big. And I like to open up with a broader discussion, just thinking about human history, because truly there's a pattern that you can recognize, and we've been benefiting from it, every single one of us, in many ways. If you go and take a look at major technological advances, which often tend to come with, you know, how power actually even moves forward as a society, these technologies are mostly based in physics. It's actually when you take a branch of physics and you move it into engineering, that is when you really unlock transformational capabilities. So you should be very happy to work on core physics, because ultimately almost all of them end up changing everything that we do. It just has this kind of really long-term effect usually. I mean, the reason we can even have these conversations today is because semiconductors prove to be so valuable. And I still believe that we're not yet seeing the end of what semiconductors have been able to bring to us. But the next one is quantum, and you can see it coming. And one of the lovely things about that is you can ride the wave. These things are really long-term, but predictable in some sense. It's a matter of when, not if. And it's wonderful because usually you don't actually know very much about how transformational these things are going to be until they happen. If you use the semiconductor physics one as an example, it is the case that if you go and take a look at what people suggested would be an application for a transistor, which is of course what drives all of our computing power today, what was put forward as one of the applications, the core applications for a transistor, compared to say a vacuum tube, was a hearing aid. They weren't thinking Facebook or Zoom, right? They were thinking hearing aids. So we can't often, although we can have a bit of confidence when technologies move into the market that things will be transformational, in the case of everything that came before, at least just pattern matching, you can't really see where it'll take you. It's going to take a few generations of people that grow up knowing and playing with these things to really see what they look like. But we have some good ideas on the kinds of things that might be unlocked with quantum technologies. And one of them is computing. And that's the one that tends to dominate the lion's share of discussion around quantum technologies. Although you could be forgiven for thinking that the word quantum is synonymous with the word magic, because it's basically used interchangeably online these days. So forgive me, I'm not going to entertain all of those, but I am going to focus on a few of these that we know of, because there's really quite a bit of hype in this space. And although quantum computers are really exciting and we have to build them because they're going to really unlock a lot, it's a disservice to us all if we overhype and have some kind of statements like that indicate that quantum computers are just going to outperform classical in every possible way, because that's not true. They're different tools. What we're looking at is an information processing device, and we know that processing information is a very powerful tool for us, and it can process information differently, because ultimately information is physical. It can be manipulated according to physical laws. You think of it as we think of digital bits as just being this kind of abstract thing, but ultimately all of those ones and zeros are represented as a particular item in a semiconductor substrate, right? So it's a particular state of matter. And so the way you can interact physically with with objects allows you to access different ways of processing information. And so the immediate law of physics that comes to mind when you think about information now is about superposition. And it is the concept that you can be in multiple incompatible configurations simultaneously. So the example that people tend to give is the example of Schrodinger's cat, where a cat could be, if it's in a box and you're not looking at it, it could be both simultaneously dead and alive. And only when you open the box do you have it collapse, quote unquote, collapse into one of those mutually incompatible states, right? So it could be in superposition while you're not looking at it. And this happens all the time, actually, for specific particles like electrons and photons, and even some larger objects for a short amount of time that can be in superposition. And superposition isn't just both. It actually is a full continuum. So what I'm trying to show here on this slide is a visual representation of not just the classical bit, which would be like a 1 or a 0 or a light switch setting, but a full continuum of states available to a qubit or quantum bit represented by a color, right? So like any tone, any shade could represent an allowed quantum state. And so long as you're not looking at that quantum state, if that you're not extracting information from it, it can exist in that superposition. And that's just inherently a much richer way to hold on to information. And where it really comes in is how these things combine. So I'm only speaking here about the opportunities for quantum computers to achieve computational tasks that can't be done any other way, okay? And I'm going to kind of try and explain to you how to think about it so that you have some guidance going forward on the kinds of things that might be suitable for a quantum computer advantage, as opposed to a classical, quote unquote, classical computer, which are really, really good. Like our classical computers are really, really good. So it's worth having a think about where the advantage for a quantum system can actually lie. And so as I alluded to, it comes down to how you combine these systems. When you add a qubit, the math that you use to add a qubit to one another is a tensor product rather than a direct product, for those of you in the mathy side of space. And what I'm going to show you is a visual representation of this, right? So no equations. If you take a look at classical information and what subset of quantum actually supersedes classical. So you can always take a classical system and encode, or a quantum system and encode a classical bit of information or set of bits of information in it. And what that would look like from the whole space of possible quantum states is like one of these white boxes here. And so for those of you who have taken enough quantum mechanics, I'm showing a density matrix. So what a classical bit, so here I'm showing what 8 bits would be. In a classical state, you are allowed to have one black dot along that specific number line, and that's all you get. So in a digital sense, those would be the two, I'm just showed 2 example 8-bit strings that you could imagine having as a state. And if you're running an algorithm, you'd be actually sampling from those different strings. You'd be flipping the zeros and ones according to a particular algorithm, right? And this compares to quantum mechanics. And quantum mechanics has a couple of different flavors. You may be familiar with D-Wave, which is an early mover in this space, where they're accessing part of the rest, like the part of the rest of this density matrix is full space. And what they start with is there's a particular kind of quantum state that they can create, and then they move things around nearly adiabatically, or they call it annealing, to arrive hopefully at an answer more efficiently that can be done with classical. But what you really want to compare it to is the full spectrum of quantum states that are available. And so we are working on a universal technology, but so is basically almost everybody else, which could, in principle, create the kinds of states that I draw here. I mean, it's not likely that you would ever choose to do so, but they would be possible. And it's mainly just an illustration to show just how much information can be packed into this is 8 qubits. 8 qubits can pack in that much information. And if you wanted to, that's where you can get these kinds of speed ups, because so long as you're not looking at it, so long as you're not looking at the quantum system or measuring it, extracting information, then it can possess temporarily an astronomical amount of information and use that to crunch things that answers to problems that can't be really done any other way. And so this is the scaling of this is where it goes. If you were to add another qubit, this goes up by a factor of 4, right? It doubles in both dimensions. So it gets really big really quickly. It would take more, what's the throwaway? So it would take more bits than there are atoms in the universe to encode 200, all the information in 270 qubits, right? Like it just goes off the charts. I think 30 qubits is what you need for the human genome, right? But when you measure it, so you'll notice it goes down to a dot at the end, right? When you measure it, you can only measure those bits out, right? When you engage with a quantum system as a classical human, working in classical scales, it only can report a particular bit string. That's the length of the number of qubits. So here you'd have an 8-bit number at the end. So it already tells you the kinds of things that you want to be looking for. And I don't mean this in a kind of formal computer science sense, but just in an intuitive sense. You have to be thinking of problems where you need temporary access to massive computational space, but that the answer is quite succinct. And so there's a few things that fall into this category. If you are inclined and you're from the computer science side of things, I encourage you to go check out what's called the quantumalgorithmzoo.org. There's a team that keeps that updated, which is lovely. It's written in beautiful math, and it's a list of all the exponential speedups that have been identified to date. And what do I mean by exponential speedup? I mean that the scaling, the low small scale values for the algorithm are kind of irrelevant. It's how it scales as a function of problem size. So one example and one of the applications that I'm particularly excited about is chemistry. And it's a really easy one to see why. Chemical objects, the atoms and the electrons therein, are fundamentally quantum mechanical objects, and correspondingly have a lot of complexity within them as wave functions, essentially. And that can't be encapsulated or even approximated very well by a classical computer. We can do okay for small molecules and small atoms, small atomic weights, but it doesn't scale at all. We don't have tools to simulate heavy elements in larger molecules at all. Because it just scales exponentially badly. Like, you're just not going to be able to do it. And so we have an opportunity to build a tool that can outperform in that it scales linearly with the system size. So if you double the molecular size, it would take roughly double the number of quantum resources to attack that problem. Which is not the way that it goes for classical. And so we can imagine doing, having proper understanding of how chemicals interact with metallic elements in a solid, or these kinds of games that just, there's no way of doing it any other way. And so I'm particularly keen on the applications within, I mean, there's so many chemical applications that we think of in terms of our daily lives, right? A lot of healthcare applications are ultimately chemical, but even, when you think about it, and I have a lot to say on this, but not today, our climate problem is, 90% a political problem, but then after, 2050, it's going to be 90% a technological problem, cleaning up that atmospheric chemistry issue. So there's a lot to be done on that side, which would benefit from better tools, simulation tools. The other one, which is interesting, is that, and it doesn't rely upon the complexity, right? So if you can go to Quantum Algorithm Zoo, that tells you all the different exponential speedup algorithms, there are absolutely applications to quantum technologies that don't rely upon that kind of exponential speedup thing. And it's just it relies on different laws of quantum mechanics. And for example, there is a no cloning theorem, which I'll get into in a bit. But what that means is that you can imagine sending signals, provably secure signals, over distances. And it allows you to, this becomes important for the following reason. The third application here on the right, which I'll speak to, is the cybersecurity one. And this is the one that will probably end up reaching people in terms of their, conversationally. Quantum mechanics will have this impact first, because these other applications are kind of infrastructure in the back end, right? Not everybody is going to be doing really high-end performance computing, but a lot of people use passwords, and a lot of people trust the internet for a lot of their, and the financial industry itself trusts that encryption will hold. And ultimately, the quantum computers are excellent hacker tools. There's a layer of every part of encryption, which is an asymmetric layer. And what do I mean by that? There's a kind of cryptography that everybody uses all the time. Whenever you send a password or anything, whenever you connect to a website or any of it, they're all using a form of encryption, which starts off with this asymmetric piece, and that is just very susceptible to a quantum computer. And we know this before we've even built a large-scale quantum computer. So there's lots of worry out there, because if a quantum computer comes online, the challenge is quite asymmetric, because one quantum computer could basically walk into whatever system it had access to. And we know, just to be a little bit more negative on it, or pessimistic on it, we know that there are lots of organizations worldwide that are saving transmission information so that a future quantum computer could decrypt it. So that's a bit nerve-wracking. So let's, how far along are we? Well, there's been a lot of really interesting work, and there's a bit of a interplay, because there's a lot of interesting work on both the network side, which can secure against quantum computers, versus quantum computers themselves, which could hack classical cryptography. And maybe I'll just say one more sentence on that, is that the provably secure quantum communications that have, but you can demonstrate, you can buy them in a short distance manner already, those are undergoing rapid development, and they can't be hacked. That's based on a law of physics rather than a computational challenge. So it's a kind of a double-edged sword, and it'll be interesting to see how these things play out. The other thing I should mention on that before I speak to where we are from a quantum computing development perspective is that there's a really intense effort to try and identify algorithms that should be secure against quantum computers. And there's been a long history of this. It's a mixed bag, because there have been a number of suggestions put forward by professionals like NIST or NSA or the rest of them as replacements to RSA, which is the de facto standard for asymmetric encryption. And it turns out the ones they put forward have all fallen to attack. So Diffie-Hellman was put forward and fell. Soliloquy was put forward and fell. Rainbow was put forward earlier this year and fell within a few months. And Psych also, they're going through this, trying to standardize on something that can hold. And this is, again, they fall into attack in the sense that known exploits exist in these algorithms. So there's still some standing, but it's good. It's a fun space to watch. It's a fun space to watch. And a lot of work needs to be done there, I think, because if we can get something that we can have trust in, then we don't need to be worried about quantum computers booting up, because we want to be able to use those as tools for all kinds of other things. And people are working at that very hard. So people have been working at what they call post-classical quantum. It used to go by the name quantum supremacy, and I'm glad that they've stopped using it as a term. But there's some beautiful work that came out of Google in 2019 that showed fairly convincingly that they were able to outperform the world's best supercomputer at a particular task, which was admittedly a useless task. So it was a useless computational task. It offered no, value. It didn't help anyone's life in any way, but it showed that a quantum computer could do something that a classical computer, the world's best classical computer, could not do. And again, this isn't like the scaling problem. This is just like what did they say? Like a 10,000x or something. And that's not the same thing as a scale it, but it shows that basically it was really exciting at the time to actually convince the world that, hey, we've gone beyond what could be done with a classical computer. And it was followed pretty quickly by a team in China doing a beyond classical experiment. This was I mean, for those of you who have volunteered in labs, I would never ask anybody to align this. Look at that, that's insane. But this was a so-called non-universal technology. So if you recall back those density matrices and those pretty pictures with the fractals, the D-wave picture is a non-universal technology. This is also a non-universal technology, but they were able to convince a good number of people that even though it was non-universal, it was able to outperform the best supercomputer, classical supercomputer. That happened really quickly thereafter, right? So 2019 and 2020. And for those of you in Toronto, Xanadu claimed the same thing in 2022, also using this non-universal kind of Chinese approach here. Slightly different setup, but still very much in the same spirit. Okay, so that all sounds like quite a bit. What I would say is what quantum computers will not do. So this is an entertaining thing. They're not going to add very well. They're actually really bad at addition. And they're really bad at well, a whole bunch of things. They're very slow compared to the 40 years of continued R&D into classical semiconductor processors. So they're not the be-all, say-all. I don't think they're going to necessarily speed up your Netflix. I don't think they're going to be helpful as better like pocket calculators. I don't think so. I think they're really going to benefit. It's a scale argument. It's the big stuff where they'll tackle it. And so therefore, from a consumer application, it's not going to be as clear cut as you'd see from the semiconductor one, at least not on the outset. There might be some consumer things that you see around quantum communications or something that could be securing yourself, your devices or something against quantum computers, but that's going to be a different play. What we're really going to see is this plug into the cloud infrastructure that we already have, right? We have a lot of, frankly, beautiful accelerators, GPUs or tensor, what were those, the Google ones, TPUs or something. These are beautiful accelerators, computational accelerators that are used for specific problems and offer like phenomenal results. And I think that's really the model for this, is that we're going to have something that instead of sending it to a GPU, you would send it to a QPU or a quantum processor and then get that result back. And it would just open up different things that you wouldn't be able to attack any other way. So different than just like, okay, let's add machine learning to this and get it better. It allows you to simulate, like, for example, the chemical one. It allows you to just do stuff that can't be done any other way, but it will be like a co-processor kind of model. The other thing that it can't do is it can't photocopy. So this is a law of, it's called the no cloning theorem. And it's according to the laws of quantum mechanics, you're not able to take a blank qubit and just copy a different qubit. You can't do that arbitrarily. You can only do it for the classical bits that live within them. And so this is already interesting because it has a few implications. One, it's the reason why these quantum networks are actually secure, because it means you can't eavesdrop, right? So if somebody were to try and send a quantum bit or any quantum particle, and then an eavesdropper could just photocopy it essentially, then there'd be a way of copying that information and then it wouldn't be secure. Ultimately, there would be ways of breaking that security. So, okay, that's good. What's the bad thing? Well, this kind of photocopying is the dumb way to do error correction. So if you take a bit in your phone or whatever, and you take a look at how it actually operates, it's not so far from a majority votes model, because stuff does happen, right? You do zeros and ones, they do get messed up. Environments do cause noise. And so what they have is just like a really rudimentary error correction protocol. Is they take one bit, classical bit, and they just copy it a few times. And then after a while, you can just take a look at them and say you've copied it across 5 bits. You can just take a majority votes, right? And if one of them is flipped, then okay, you flip it back. And so you basically built redundancy into your system. But you can't do that with these. You can't take a quantum bit and copy it and then just say, okay, off to the races. So the way that error correction works is like the whole reason why we don't have a working quantum computer yet. It's hard. It's just there is a strategy for quantum error correction, but the ask to deliver it, instead of using basically standard duplication, you have to basically entangle your system across a few other qubits. And there's a lot of really beautiful math that goes into thinking about how to manipulate quantum information in that format. And the demands that are placed on people that are trying to build these things are really, really high to be able to hit those kinds of error correction goals. So there's a few results that are coming out from different sites over the past year or so that are claiming things around error correction, but I would say that it's still a very it's an ongoing process, and not anyone is really over that line yet. There's a lot to be done. So just back to the networks game, what that means also from a networks perspective is that I said that you can do these quantum communication channels, and that's true. But once you lose a photon along the way, that's it. You can't amplify either, right? So you can't eavesdrop. Okay. Error correction's hard. Okay. The other consequence of no cloning theorem is that you can't have an amplifier either. And so if you wanted to set up a global quantum internet that can, you can have provable security over short distances meaning like maybe 100 kilometers or 400 kilometers if you know what you're doing. That's okay, but you can't like boost your signal and send it on, because that would require amplification, which would involve photocopying. So what people have been building, in China in particular, have been really on top of this, is building out networks, but they have these so-called trusted nodes in the middle. So you have to basically trust that nobody has hacked these nodes. And then otherwise, you can have these quantum signals distribute at large. But what's missing is what's called a quantum repeater. And people, including us at Photonic, we're trying to build these things because then it's the quantum version of what an amplifier would need to be. It allows you to distribute entangled signals and quantum columns at larger distances. And that's another active area of research, because then you could imagine truly teleporting information from anywhere to anywhere else in the globe. And it's just wonderful to be able to say that with a straight face. Like, it's true. We're going to try it. We can teleport information over short distances. What we're missing is global entanglement, the ability to get entanglement around the whole place. Oh, so yes, this error correction thing is a little bit interesting. And I did promise to end a little bit early. And I have as I said, a hard stop in 20 minutes. So I will maybe aim for 5 or 10 more minutes and then open it to questions. But before we do into that, just a few more things on where things are at in the quantum computing space. This was a picture that came out from Google 2019, where they indicate, okay, well, fine. So we don't have error correction now. It's really, really hard. What can we do between now and then? Now being at the time when they drew this, they were at the kind of like 10 to 20 qubits level. And those are equivalent to a laptop. So yes, 30 qubits is equivalent to a human genome, but it's 10 qubits you can do on a laptop. So we were stuck in the kind of 10 to 12 qubit range for a while until Google kind of came through to 50. But the question was, okay, so is 50 enough for error correction? And according to their thinking at the time, the answer was no. I disagree with this. I have other tricks up our sleeves, as it were, but it's still a useful diagram to show, the gap between where we are and where we need to be for error corrected stuff to implement the kinds of algorithms that we're all excited about, the chemistry algorithms, or even the hacking tool algorithms, which is called Shor's algorithm, is the famous one to break RSA. So this is where Google decided where it wanted to go. It wanted to go check out this kind of few hundred qubit level, and that's where it's spending its time. IBM is also there now in that kind of qubit count level. But it's not just a count game. You can see the axis here. It's not just about having buckets of qubits. It's about having buckets of gray qubits. So you need to get the error rate way down. And there's different strategies for different teams. At Photonic, we're going to talk, maybe I'll get a bit of time to talk about it, maybe not. But our picture is to start at a large number of qubits and then just drive down on the error rate. So that's kind of more of our trajectory. But the near-term applications has been really interesting because it wasn't known, right? So if you have say you have 1,000 qubits and it's a low error rate, can you do anything interesting? Can you do anything valuable? Because it's kind of more like an analog system. And perhaps if you get the error rates low enough, there might be something interesting. So there has been, a lot of effort put into trying to find useful, right? What's useful? It's not just able to do something that a classical computer can do, but, can you actually predict something or calculate something of use? And it's been an open question for the past couple of years, and it doesn't seem to really have gotten much traction. So it was an unknown, right? Because you can't simulate it. You can't figure it out in advance. So it's been a fun thing to watch. Now, this is an interesting one. This is, despite the history, right? So we're at, I don't know, I think the world record right now is, the public world record, I think, is IBM just started talking about their 433 qubit chip, but they do offer access to their 127 qubit chip. There's a few neutral atom companies that can have, at least in one place, 300 qubits. That kind of number, most people are way below that. Now, that is completely different from the kind of million qubits people are thinking of that you'd need for an error-corrected RSA attack, right? So how likely, this is a survey of a whole bunch of different specialists in the field with their projections on what's the likelihood that RSA will fall in this time frame. And if you take a look at the history of quantum computing and the number of qubits and the fidelity of those qubits, none of these projections line up at all with like the linear fit to those numbers, right? We've had 12 qubits in 2001. And now we're at like a couple hundred. That's nowhere, like, does not at all scale. They're kind of building in some kind of exponential scaling assumptions here, which haven't actually shown to be the case at all over the past 20 years. So it's interesting. It seems to be the case that most of these experts expect a curveball to come, and they just don't really know when. And when there's that curveball, these things will unlock quickly. So we're going to have to see how it goes. But experts are also not very good at predicting the future necessarily. So it's just an interesting data point. If you want to go take a look at this is from, I think it's called the Evolution Q survey. So you can go Google that, Evolution Q Quantum Computing Risk Report, I think is the name of it. Okay, and so in the last maybe like 3 minutes, I'll talk a little bit about what we're up to out in Vancouver, although we do have people that work in Ontario near you and in Quebec and Alberta as well. There's a whole bunch of different platforms that are out there, and we're in a really interesting phase in quantum technology development because you can kind of look to previous technology events or big technological shifts and get a pattern for it. And so what usually happens is you have 20 years where things are in academia, and then there's like this explosion of startups and commercialization activity, and a whole bunch of different approaches come out. And I think that's where we're at right now. In quantum. But then what usually happens, and this is played out for like TV and railways and cell phones and all this, there's like this emergence of a so-called dominant design, or like a consolidation where everybody starts agreeing like, oh, this is the winning one, right? This is the strategy. We're all going to agree and work on this one. And then there's this substantial consolidation event, and it kind of slowly trickles down to about 4 different companies. So it's not there at all for quantum. There's buckets and buckets of companies, and a lot of them are just variations on a theme. So these are the kind of, I pulled this from a 2019 paper, which is great because that means I didn't have to be the one to write the for or against. I disagree with most of these things, but it's still helpful to indicate, these are the kinds of platforms, physical platforms, right? Because after all, this is physical information. These physical platforms that people are trying to build quantum computers out of. And what's distinct about our approach, and again, just to kind of summarize, our approach is we are combining two, actually. And it's not often when you combine 2 quantum platforms, it's the worst of both worlds, not the best. But what we're seeing here is that the small footprint of silicon spins actually couple really, really nicely. When you get them to talk to photons, then you can couple them in all kinds of different ways, which is really, really helpful for many, many reasons. But it means that, it's a lot easier to scale. So we've been able to, in terms of qubit count, we've been able to produce in our Nature paper earlier this year 150,000 qubits, and those aren't wired together, right? We're not promising any of that. It's just saying, hey, look, you can print them. And with silicon, it's as easy to print 10 as it is 150,000. So we did the bigger number. But you can go and talk to each of them, and they can each talk to photons, which means they can talk to each other in principle through those photons. And that's the approach that we're taking. It means that we don't have to worry about if you lose a photon, you lose a qubit, which is what you have if you're working with this integrated optics approach. So I think, yeah, just to kind of conclude, that's where we're at. We're kind of in this interesting middle point in this Venn diagram of two different silicon approaches, because of course silicon is not just the classical semiconductor technology that we're after, but the pure photonics approach also is a silicon approach, because integrated photonics as well as integrated electronics is now a silicon thing. It's just because silicon is just really good for all of these things. So yeah, we are a spin photon interface working in silicon, and there's lots of content on this to go take a look at if you want. And I encourage you to reach out if you're interested in more things. I'm going to stop there though, and just open it to questions.
Yeah, thank you, Dr. Simmons, for the amazing talk. It was really nice to get started with our conference with this broad view of the quantum computing field and where it's at right now. So yeah, we do definitely have time for questions. We'll be taking in-person and online questions. So if you are attending this online and have a question, please put it into the chat. But we can start with an in-person question. Yep.
Is a quantum computer Turing machine?
It kind of goes beyond the Church-Turing thesis, if you know what that means. So it's richer.
Yeah.
So what exactly is the errors we are talking about? Let's say in a classical computing system, we do error correction when the data is in transition, it goes from one system to another. So let's in an isolated quantum computer, why do we need error correction at all? Is it the observers? Are they not like precise enough for the measurements? Like what exactly are the errors?
Yeah, so the great question. So mostly it depends on your system, but there's a few sources of error. When you're working with a superposition, information eventually leaks out. So a cat can't remain dead and alive at the same time, actually for very long. And for quantum systems, it's called a coherence time. So what that means is that eventually these systems, the information leaks out to the environment, and that constitutes a measurement, and that constitutes a natural decay or a natural error rate for all of these quantum systems. So that's one. Some systems like the spins in silicon are just phenomenally long-lived. Like we've set records for that stuff. So that's not the issue. The issue for the errors come about from control. So if you have, if you remember the visual at the front where a pixel, any color and any tone represents the quantum state, manipulating your quantum information is essentially an analog rotation. And you can think of it as a sphere as well. There's lots of representations of quantum information, but every time you mess with the quantum system, it's like an analog rotation. It's a really good way of thinking about it. And that is never perfect, right? It's never to the parts per billion level. It's an analog control. So you have user error, which comes about from that. And you also have just inherent decoherence. And in addition to the one you mentioned, which is spot on, there is measurement error. There's initialization error. Like everything's imperfect slightly, so.
So if there is any time for a super short introduction to this, I'm not totally sure. I'm trying to think about my question. In your research, what does in general the sort of coupling between the incident photon and the silicon spin look like?
Perfect. No, that's a great question. So yeah, these are spin photon interfaces. They also go by the name color centers. And we're standing on the shoulders of giants here, because there's lots of color center work that came before us, just not in silicon, not much in silicon. And there's ways of getting defects to emit light And you can think about this, the closest sister color center are actually NV centers in diamond. And the way that you know that they emit light is that if you take a look at diamond that has a whole bunch of extra nitrogen or NV centers in it, it actually emits, I think it's either blue or yellow, I forget. Oh, I should know this. But that's what gives the diamond its color, right? It is actually emitting light of this wavelength because it has all these defects inside, which naturally emit photons of a certain wavelength. And so for these centers, they're emitting in the telecom band. So they emit telecom light, which is great because then you can then use telecom stuff to link them all up. But the photons themselves are good qubits. So you can have them, you can trigger them to emit a photon, and then those photons can be entangled with the spins they leave behind, which is super useful. You can also, if it has a strong interaction with light, you can actually reflect the light off of it and acquire a spin-dependent phase shift. That's been demonstrated in other systems. So again, we don't have to invent all of it, but there's lots of different ways. So long as that has a strong interaction, like that's the key. It has to interact strongly with light in one way or the other, either in reflection or emission. And then you can play all these kinds of games.
Right. So the system emitting light is basically inherent in the fact that the crystal has impurities, I guess.
It's the specific impurities that we're making. Yeah. So there's always impurities and everything, right? But these ones we're picking and making specifically because we know that they have this property in their interaction with light.
Awesome. Thank you very much.
Yeah, my pleasure.
We'll have time for one more. Yeah.
It's a shame I can't see you all.
Hello.
Hi.
So in the problem you said about the error correction. So when we are sending a qubit quantum information, we sometimes miss a qubit and we cannot like find a qubit and build an amplifier. So is it possible that when passing the information, we also at the same time we pass the size of the length of the information in the traditional classical way through the traditional way, and in that way, if we found out that in the end the information we received in qubits is missing 1 or 2 bits, we can ask the sender to resend just in like original HTTP requests, things like that.
There are error correction codes that deal with specifically erasure channels, which is what you're describing. They're a bit different from the ones that are protecting against control errors, right? And they're not exactly the same as the classical ones, but you can imagine them as a quantum variants of them. They're still very demanding, still very, very demanding. And yeah. But at the same time, it's just a different error channel that you can protect against. Yeah.
I see. Thank you.
Yeah.
Yeah. Thank you, Dr. Simmons, again for speaking at our keynote for day one. And we hope you have a great day.
Yeah, you too. Have a fun conference. Sorry I couldn't be there in person. And thank you again for inviting me. It's been fun.
For sure.
Bye.
Thank you.